Okay, we're going to finish talking about the idea of titrations and figuring out the concentrations of unknown substances and getting used to using the equation. But again, it's not a complicated equation, and it's something that is similar to what you've seen before. So is also very similar to those dilution problems that we did with concentration in the formula. So it looks like that. And it also looks like the gas laws where you are comparing two things on either side. So you watched the video on the titration, gave you a little bit of an idea of how that's done. Just a couple of things regarding the tools and equipment that you would use as a review from the video. An Erlenmeyer flask is best, which is the almost triangular looking flask that has the thinner neck, because it prevents sloshing. So that narrower neck prevents your liquid from sloshing out, as opposed to an open beaker, which is just like a cup. As you guys know, we've used beakers all through this year. So the Erlenmeyer flask is important. Keeps the liquid in, because you need to have an open top. You can't, it's just annoying to cap it every time you swirl. So tube is called a burette. You never used a burette, and mostly those are used for titration. Since we didn't do a titration, you did not use a burette, and but you use a burette clamp, tighten it on, attach it to those ring stands that you have used when we were using the burners and trying to heat things up on those ring stands. And then you clamp your burette to that. And then it's almost like I think she said maybe a straw almost. And then you have the stopper at the bottom, and that allows you to slowly add the liquid to the Erlenmeyer flask, okay? And you do have to go slowly at times, because if you add too much, then there can be a huge pH change. And what you want is a very gradual pH change, and you want to go just to the endpoint, which is where that change is detected. You don't want to go way past the endpoint, because then you've added way too much volume and it skews your calculation. So you want to take that liquid, add it just to the endpoint. So that's why you're adding a few drop or two, swirling the flask with the indicator in it. Now in the video, she used a universal indicator, another very common one for, especially if you're using a strong acid, or and if you're titrating a strong acid and a strong base, which she was too. She was titrating sodium hydroxide and hydrochloric acid. Another very common one for that is phenolphthalein. And that's because you have two color choices. Whereas universal indicator, you kind of had the rainbow, and depending on the pH, you could use that indicator card and match it up. With phenolphthalein, it's either clear or pink. And with phenolphthalein, what you want is it to go to a very, 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 very faint pink. And what we are taught in a lab when we use phenolphthalein is to take the flask and take a blank piece of paper, because it's clear. And so you add a few drops, you swirl, you add a few drops, you swirl, and then you take your Erlenmeyer flask and you hold it up against a piece of white paper. And that will help you detect any change between clear and just a very faint pink, because you really don't, if it's bright pink, you have added way too much, and you will get points off on your lab, because this instructor would say, you rush this is not correct, and it will give you a very inaccurate response. Okay, so let's get down to the equation that you're going to use. There again, this is to find the concentration of one of the unknown substances in your titration. So you're going to use the molarity of your known substance and multiply it by the volume of your known substance, and then you're going to set that equal to the molarity of the unknown times the volume of the unknown. And what you're going to look for, also pay attention to this, is that sometimes, as you know, it's not a 1-to-1 ratio, and sometimes an acid, it might be like sulfuric acid, where it's H2SO4. That makes a difference. You also might have, and we'll look at a problem like that. I think the one I've given you is a base, but like something like barium hydroxide, BaOH2. Well, that 2 as a subscript on the hydroxide means it's double the amount. you have to take that into account. And there's a problem that we'll look at. So the number of equivalents is important. Know this formula. Okay, so here's a couple of problems. So a volume of 108 milliliters. So here's a volume, known concentration. So we have a volume of 108 milliliters of a 5 times 10 to the negative third molar solution of sodium hydroxide can neutralize, meaning you go from basic to neutral, pH of 7, 36 milliliters of nitric acid. So if you think about this, what you're doing a neutralization reaction, and you're going to make a salt and water. Okay, and you want to do that to the point where it's neutral. Otherwise, it's not a neutralization reaction. So you want your pH to be just at 7. So what we want to know is if it took 36 milliliters of the acid, what's the concentration of the nitric acid that you place to neutralize it? So let me pull up. I'm going to share a whiteboard with you for just a second. So we're going to look at sodium hydroxide reacting with nitric acid. Okay, so we're going to take sodium hydroxide. So let's look at what our salt would be. Okay. Sodium, positive, nitrate is our negative. So our salt is going to be NaNO3. Now I do want you to notice this. This is already balanced because sodium has a 1+ charge, hydroxide has a 1- charge, so your subscripts will be 1. Nitrate has a 1- charge as a polyatomic ion, and hydrogen, as you know, as an ion has a +1. So we don't have to worry about any coefficients or any additional subscripts other than what's in the polyatomic ion. So our salt, we take the cation and the anion from the acid, cation from the base, and we get our salt of sodium hydroxide, and then of course we make HOH, which is water, okay? So that's the reaction that's going on there in that problem. All right, so here's our neutralization. We made a salt and we've made a water. So now let me go back. So how do I fill this in? I've got a neutralization reaction. I know 1 volume and I know 1 molarity. And I'm going to keep the volume in milliliters because they're both in milliliters. So that's okay. It doesn't make, you don't have to convert that to liters if they're both in milliliters. So molarity of my base times the volume of my base is equal to the unknown molarity, which is the molarity of our acid, times 36 milliliters. And so then you go ahead and do this multiplication and divide by 36. And then that's going to tell you that the concentration of your acid was 0.015 molar. Okay, just a real quick multiplication and then a division problem. All right, now let's look at this one. Now this one is the same idea. We're going to look for the concentration of the acid. Let me fix this real quick so that's not confusing. But I want you to notice something. I've already gotten this equation written out. So adding 38 milliliters of 1.5 times 10 to the negative 2 molar barium hydroxide. So we know the concentration, and again, we know the concentration of the base. Okay, sometimes you'll know the concentration of the acid. That's just the way this problem's laid out. And we know that it can neutralize 20 milliliters of hydrochloric acid, but we want to know what the molarity of that acid is. That's our unknown. That would be our titration problem, figuring out the molarity of hydrochloric acid. So I want you to look at this equation. How did I know barium hydroxide was BaOH2? Well, I know it now, but if I were you, I would go to my periodic table. I would find barium, and now when you do that, you will see that it is a group 2 metal, which means when it forms an ion, it gives up 2 electrons to become barium 2+. Hydroxide is always 1 minus. So that's how I know that I need to have my subscript here. Then it's hydrochloric acid, which is HCl. Now watch. When you redo the equation and you make your salt, it has to be BaCl2 and then water. Water is always one of the products in a neutralization reaction. Okay, so here, you need to watch this to make sure you do your calculation correctly. All right, so BaOH2, 2 oxygens, 2 hydrogens, has to be balanced out, and you have to have 2 chlorines over here because barium is 2+ charge. So to balance this out, we can put a coefficient of 2 there and a coefficient of 2 there, and now it's all balanced. Now watch what happens in your calculation. So I know that I have 1.5 molar barium hydroxide. Okay, what do I care about that's making that basic? Do I care about the barium or do I care about the hydroxide? I hope you know what makes it basic is actually the hydroxide ion, not the barium. So that's what I care about. Well, if my overall concentration of barium hydroxide is 1.5 times 10 to the negative 2, you need to think, this is a solution. That means it's dissolved in water. So what's really happening? So I'm just going to isolate the barium hydroxide for a second, and I'm going to share a whiteboard with you and look at that. All right, so we're going to treat barium hydroxide and just look at it by itself. Now, it has a concentration, so we know it's diluted. All right, it's mixed with water. So while it's in water, even before you add the acid to it to get a reaction, this is happening. Okay, that's always happening because it's in water. Now, you haven't even added any acid yet. I mean, you will as you start your titration. But while you have your barium hydroxide solution, this is really what's going on in there. So if you have a 1.5 is it times 10 to the negative, sorry about that, 2. So 1.5 times 10 to the negative 2. Concentration, what's going to be the concentration of hydroxide? Well, it's a 1 to 2 ratio. So you have to double this in your calculations. If this is 1.5 times 10 to the negative 2 molar, this is going to be twice that, or 3. So 3 times 10 to the negative 2. And that's the value you have to use in your problem. So let's go back and look at the rest of the problem. Okay. So notice that my molarity is not 1.5, it's 3 times 10 to the negative 2. Then because of that breakdown, that dissociation process that's occurring. So then I know I have 38 milliliters of it from the problem, so there's my. Then I'm looking for my unknown, and I'm going to multiply it by 20 milliliters because that's how much I used. Again, now I multiply and then I divide, and I get a 0.057 molar solution of HCl. All right, I'll stop there. And I will look for problems to practice with. And I hope you guys have a great holiday weekend. And you can expect some sort of, there's just a few more little things I want to mention about buffers, and then we'll be done with material. So this is a pretty good place to stop. We've spaced chapter 16 out pretty well. So you can look for just a pretty short video to wrap up this chapter on Tuesday. And we will have a last, call it a knowledge check, skills check maybe, probably Thursday, just to wrap it all up. And it'll be quick. but I feel like we need to tie a big bow around, around chapter 16. But that'll be it. And I hope, again, you guys have a great holiday weekend. I miss you. Hope to see you soon, as always, and keep pushing hard, just a few more days.